Welcome to your Daily Dopamine with Dr. Joe McCullough, where we deliver daily doses of education, entertainment, and inspiration. So sit back, relax, and get ready to be dopamine.
Hey, welcome AV Exec. Turn this around, Mr. Universe. Okay, we are back with our weekly Ask a Physicist Anything with Paul Graham. My name is Joe McCullough. I'm the physics program chair at Cabrillo College. And every Wednesday, 3 o'clock Pacific Standard Time, we're doing Ask a Physicist Anything. Today, we're going to talk about Hawking radiation. Hey there, Mr. Universe, welcome. Right now, it's just you, so this is personal to you. I think me not broadcasting. Lily, I was wondering if Lily was going to join us. She's one of our regulars. Welcome. So we are back. I think this is episode 9, and I actually haven't posted the last episode, so I will do that really soon. Welcome, Lily. Welcome, Brian. Got my new phone. Yes. How's the sound quality? Sounding good? Yes, yes, yes. Okay, so I'm going to turn this around and give you to Paul. Today, we're going to be talking about Hawking radiation and anything else that we have time for. All right, Paul.
All right, excellent. Great to see everybody again. Sorry about the sound quality last week, but we'll give this another try and see if we got the technical difficulties sorted out. Among the questions that we've gotten a few times as this has gone on has been Hawking radiation, which, as a lot of you probably know, this is the radiation that actually means that black holes are slightly misnamed. They are not perfectly black. They are not incapable of radiating light back to the rest of the universe. In fact, if Hawking is right, and we think these days that he probably is, every black hole is actually constantly radiating from every square meter of its event horizon surface area. And the black holes that we can easily observe astronomically these days, the big ones, and by big ones I mean at least the mass of a star several times the size of our sun, because a star that size at the end of its lifetime would collapse into a black hole. Or better yet, the gigantic black hole that resides at the core of every spiral galaxy like the Milky Way. And we're pretty confident that, the data supports that idea these days. These black holes are radiating incredibly tiny amounts of energy from their event horizon. It's as if the event horizon was a surface at very, very close to absolute zero. However, if you've got a much smaller black hole, either because one of the large ones shrinks over eons so vast that I don't even have a word for numbers that big, because they would shrink very, very slowly, or because you got a black hole that started out small in the first place.
A primordial black hole.
A primordial black hole created in the early universe, or if it is possible, as it turns out, to create miniature black holes in particle colliders. It should be possible eventually. We think it's probably not right now. It's only certain very long shot versions of string theory that predict, hey, maybe you can produce them at the energies that we can do right now at CERN. These black holes would be incredibly hot. The smaller a black hole gets, the hotter it becomes, the higher the temperature that its event horizon surface acts like, and they would radiate away their energy almost instantly in a very high temperature flash of gamma rays.
And in fact, just throw it out there, one of my projects on my thesis was searching for primordial black holes using a new gamma ray detector.
Is this the one that's in orbit now, or?
No, this was a water Cherenkov detector.
But there is one in orbit, isn't there? And that's one of the, I'm now blanking on the name of that space telescope that's up there looking for gamma ray bursts. But one of the things it's looking for, I believe, is primordial black holes as they reach the end of their lifetime and emit all the energy they've got in one giant flash of gamma rays.
Yeah, Mr. Universe, I was looking for gamma ray bursts using a new type of telescope called a water Cherenkov telescope, and I did a blind search for any new sources of gamma ray bursts, and I also looked for exploding primordial black holes, which Paul's going to tell us how could they possibly do that. Before we do, let me turn around real quick. So for those of you joining, we are doing our Ask a Physicist Anything with Paul Graham, and today we're talking about primordial black holes. And a couple things. If you have questions for Paul, type them in. If it's appropriate, I'll sort of stop him and ask the question. If not, that can go on the topic for next week's discussion. And if there's something that you come up with, you want to ask a question, go to my YouTube channel, search for Joe McCullough, comment on one of the Ask a Physicist Anything videos, and then hopefully we'll get to that. Okay, back to Paul.
So a quick review of what we mean by a black hole in the first place. This was one of the first things that we tackled at the beginning of the Ask a Physicist Anything series when we were talking about the movie Interstellar.
Which Paul loves the actors.
I was about to say, man, I don't really object to the science. I mean, parts of it are wrong, but the fact that they even tried to do that kind of science in a movie was awesome. But yeah, I wasn't crazy about the acting. But as we reminded you back then, what we mean by a black hole is, well, in general relativity, in Einstein's model of gravity and the way gravity actually reflects the curvature of space-time, any place where you've got any amount of energy. Now, mass is a very concentrated form of energy, but actually any kind of energy will do the trick here. Energy always pulls the space-time around it into a curved configuration. If you look at the shape I'm miming, it's kind of that funnel that you always see on those YouTube videos where they show space-time kind of contracting into a funnel around a black hole. Now, it's not just black holes that do this. The gravitational field of our planet can be modeled as a much more shallow funnel that then levels out again as you get inside the planet, and they've got the mass pulling in every direction, so it doesn't actually fall to a singularity the way a black hole does. In a black hole, you actually take all the energy that collapsed into making this, and if you concentrate that energy into a small enough region, you find it is then literally impossible to stop it from collapsing further. I think we talked once about the fact that essentially once you've distorted space-time far enough, you tilt the space and time axes to the point where the direction that we consider inward toward the center of that black hole is the direction that locally, if you're living in this region of space-time, you consider the forward direction in time. So time actually points inward rather than toward what the outside world would think of as the future. So since obviously as I'm standing here, I have no way of stopping myself from continuing to move forward in time. If I were living in the space-time inside that black hole, I would have no way to stop myself from continuing to, as measured from the outside, fall inward toward the center. I wouldn't even really think of that as a motion through space. I would think of that as just a motion toward the future. There's not a damn thing I can do about it. Now, when the region where it becomes inevitable that you will continue to move inward is what we call the event horizon of the black hole. If you are outside that event horizon...
Which is a movie you should see if you haven't.
Which is another movie, yes.
Not really good.
Not all that great, but...
Great title.
Yeah, and I mean, hell, I like it whenever people bring up these topics in a movie. The thing I was sad about in Interstellar was I just kind of felt like, man, all these characters are supposed to be scientists. They're not acting like any scientist I've ever met. They're not curious about all this shit. They can barely, manage the enthusiasm to say they've got a question about it. But in any case, if you are outside that event horizon, then it is possible, maybe not easy, but possible, to climb your way back out into normal, the normal flat space that would be distant from this black hole. Again, time would be passing very slowly for you down here. You could say your time axis has almost turned around to the point where it points inward, but not quite. So you still can.
Funny comment. Lily says you should do a YouTube series where you rant about sci-fi movies. That could be a whole nother series.
My rants about sci-fi movies probably aren't as entertaining as the tricks that nature itself can pull here. So I'll stick to the physics for now. But yes, if you get me started, I will rant about those movies. But we've got limited time. So
have you seen The Core by any chance?
Have I seen what?
The Core. Where they drill down to the...
Oh, The Core. I thought you said Quark.
No.
Oh, I haven't.
You should watch that one.
I should. I've heard that it's... I don't know if good is the right word, but I've heard that it's definitely worth watching.
It's horrible. What do you think of The Martian? Actually, that may be...
Oh, The Martian I think is supposed to be awesome. Yes, I
haven't seen it yet?
But I will.
You got to read the book first.
Yeah, that's kind of why I haven't seen the movie yet, is I keep saying, I got time to read the book first. But in any case, if I'm right outside that event horizon, none of these pens are actually working. If I'm right outside that event horizon, it is possible for me to escape to infinity. Might take a lot of energy to climb back out of that gravity well, but it is not impossible. Once I'm inside the event horizon, I can't even try to climb out of the gravity well. It's not like I try, but I fail because my rocket engine's not strong enough. Once I'm inside the event horizon, time is again pointing inward toward the center. And I don't care how big a rocket engine you hand me and which direction I'm allowed to point it and turn on the exhaust. If you tell me, yeah, use that rocket engine to propel yourself into the past, I'd say, man, I'm not exactly sure which way I'm supposed to point the exhaust end of this rocket engine to propel myself backwards in time. That's what it would be like if I were trying to climb out of that black hole. So once you fall in, you're in there for good.
You're screwed.
Now, classically, what this means is there's an old saying in physics, well, not that old, because it only dates back at least until general relativity came out, which is almost a century ago now. So there's a kind of old saying in physics that black holes have no hair. Now, what they mean by that is if you are outside a black hole, it doesn't have any interesting features that distinguish it from any other black hole. The only things that you can actually measure about that black hole from outside are how much mass does it have, or if you prefer, how much total energy does it have, because they're interchangeable, how fast is it spinning, and what is its electrical charge. And by the way, the answer to what its electrical charge would almost always be 0, unless you've got a really tiny primordial black hole. So the only really two questions for an astronomical black hole are how much mass does it have, and how fast is it spinning. And that's all the information there is. When they say the black hole has no hair, what they mean is it doesn't have any features other than that. There's no other information that you can tell me about it. Now, the reason why this is a bit of a head scratcher is, remember, we talked recently, for those of you who saw our entropy video, about how the amount of entropy in the universe, according to the second law of thermodynamics, is continually increasing. And we said one way of thinking about what entropy means, I mean, you hear entropy means complexity, entropy means disorder, randomness on a molecular level. Another way of putting it is entropy is how much information you would need to specify the complete state of a system. And what we mean when we say the amount of entropy in the universe keeps going up is essentially the universe is getting more and more complicated at a molecular level. Patterns are breaking down, being replaced by more random patterns, and the amount of information I would have to write down to tell you what state the universe is in right now is continually becoming more and more information, because the patterns are breaking down. I can't say, oh yeah, this part of the universe is behaving just like you'd expect. Well, no, instead I've got to say, man, each atom's doing its own thing, and the book of the current state of the universe is continually growing to be a longer and longer book. However, this looks like the one exception. If I were to take any system with information, I take a jar of gas. Now, right now, if I wanted to specify to you where every molecule in that jar of gas is and how fast it's moving and anything that's unusual about one of them than the other, like one of its electrons is in an excited energy state or something like that, I would have to write down a lot of information to tell you about that jar of gas. It contains a lot of entropy, in other words. I drop that jar of gas into the black hole. Maybe it still exists beyond the event horizon, but from out here, all I can tell is the mass of the black hole just went up a little bit. All of that information about what was going on internally with the gas seems to have vanished from the universe, or at least the part of the universe that I can interact with. So by dropping that thing into the black hole, it looks like I actually made the entropy of the universe go down. Now, in a way, I suppose that's astoundingly good news, because we said that the second law of thermodynamics is what eventually, in the very distant future, leads to what they sometimes call the heat death of the universe, which kind of sounds like a line from a Calvin and Hobbes cartoon, the giant space kablooey that ends the universe or something. What they mean by that is not some huge conflagration that incinerates the universe. They actually mean heat in the sense that everything comes to thermal equilibrium. The universe cools off to a boring, lukewarm gas, in which there's all kinds of stuff going on at the molecular level. Every atom in that gas is doing a different thing. But from the point of view of us as multicellular creatures that need a certain amount of order in order for us to exist, we would say that's such a boring universe, it can't even support us, and what's more interesting than us? But So, that's kind of a dismal long-term prognosis for the universe. I figure if our descendants actually survive that long, they might be so zenned out by that time on the sheer wonder of creation in space and time that the fact that it ends at a certain point and becomes boring might just be like, one more interesting feature from their point of view. But in any case,
what happens to black holes at that time? Well, we're going to get to what's happening
So
once we get to Hawking radiation, which Paul will be getting to at any point in time now.
Because if it is possible for me to decrease the entropy of the universe, hey, I just found a loophole in the second law of thermodynamics. Maybe not a very useful loophole to me right now. I say, what am I going to do about that? Like throw all the matter in the universe into a black hole and say, therefore, I've saved the universe from the ultimate heat death? Isn't that what was the old saying from 40 years ago or something? We were forced to destroy the village in order to save it. Well, but you figure if there's one loophole to the second law of thermodynamics, there could be others. So this was kind of an interesting point. Well, Hawking came along and said, no, actually, I don't think you do remove that information from the universe. Because he said, when we said black holes have no hair, we're forgetting one thing. If we just use general relativity to describe them, then yes, it does seem like the only features they've got that are measurable from the outside are their mass and their spin and their charge. But he said, well, let's not forget about quantum field theory that we were talking last time when we were talking about that exchange of virtual particles that lets two electrons exert a force on each other. For those who weren't here, what we were saying in brief was that what we call the vacuum, empty space, is not at all empty. What's going on all the time in the vacuum is, out of nowhere, a particle will pop into existence. Let's say this is a virtual electron. Now, if the electron popped into existence, then automatically, along with it, a positron, its antimatter partner, has to have popped into existence as well.
Write that a little bit bigger, Paul.
Oh, okay. So we've got an electron popping into existence right there.
Quantum foam, yes.
Yes, quantum foam is what we call this foam of particles frothing out of the vacuum. And by the way, on all of these Feynman diagrams, time runs upward toward the top of the diagram. So this is the future, this is the past. So that electron pops out of nowhere, and along with it, maybe even in a different color, a positron pops out of existence also, or pops into existence also. And the way we draw this is the line for a positron is the same as an electron line pointing backwards in time. There's a deep symmetry in there between time, future and past, and matter and antimatter that would be a topic for another day. But if these are virtual particles that were created out of the vacuum, there was no budget of energy or momentum available to create those particles, but the universe created them anyway. Well, they can't last for very long. They will disappear back into the vacuum. The electron and the positron will come together, and they will do what electrons and positrons always do when they meet. They will annihilate. Actually, I don't even want to put a virtual photon there. I want to say that's just a closed curve. But they will annihilate and pop back into the vacuum.
So they can pop out of the vacuum and live as long as they're not violating the Heisenberg uncertainty principle.
Yes. What people will sometimes say this means is you can violate energy conservation as long as you do it for a very brief time. And the amount of time would be saying, well, the amount that you violate energy conservation by, multiplied by the amount of time that those particles last, has to be limited by Planck's constant, which is a very tiny constant of nature.
Mr. Universe, we'll get to that at some point. He wants to know what happens if black holes have opposite charges, and not even sure that
they will actually attract each other, although if we're talking like celestial-sized black holes, the amount of charge you can load onto one is usually pretty tiny. So to try to take these massive objects and let them pull toward one another and accelerate toward, you're going to have to wait a very long time before you notice them moving at all. But yes, they will exert that force on each other. Black holes with charge do create electric fields the same way anything else with charge creates electric fields.
So Planck's constant is on the order of 10 to the minus 34?
10 to the minus 34 joules times seconds, yes.
So just to give you an idea, we're talking about these virtual particles existing for tiny, tiny, tiny times.
Now, I do have to say, though, I do not like that interpretation people give where they say the law of energy conservation was violated for that brief amount of time? No, it wasn't. The law of energy conservation never has an exception as far as we know. And when you look at field theory, the equations that talk about this quantum foam, well, at every one of these events where you have a particle and antiparticle line meet, one of the little pieces of mathematics that you put in there as you write the thing that you're going to have to integrate to find the probability of this is what they call a Dirac Delta function. This little guy, named after Paul Dirac, an awesome physicist from the 20s and 30s. And one of the Dirac Delta functions you multiply in is saying the total energy of those particles has to be zero. The way the Dirac function works is its value is equal to zero almost always, unless the number you plugged into it was zero, in which case the Dirac function shoots to infinity. I love the Dirac Delta function, precisely because I get to scoff in the face of the mathematicians who keep saying, oh, infinity's undefined. You can't the Dirac function's equal to infinity, but only if its argument is zero. What that means is the total energy of all of those particles, and I guess what I should really say is the total energy coming out of that vertex minus the total energy going in has to be zero. You can't, no new energy was created or destroyed there. So yeah, I would say no, energy conservation was not violated. What was violated is this equation from relativity that says, hey, the energy and the momentum of a particle should be related by this mass hyperbola, as they call it. The energy squared equals the momentum squared plus the mass of the particle squared. I should actually be putting in some factors of the speed of light there, but what the hell, we're among friends here. We're going to just use c equals 1 units. We're going to say the speed of light is 1. I will tell you another time why we are not actually insane when we say in physics, oh yeah, treat the speed of light as 1. It actually, it makes sense. But for now, that's just my excuse for not writing in the c squareds. But you've got this hyperbola where if you plot the energy and the momentum of any given particle, it should lie somewhere in that hyperbola. And for a particle that lasts any decent amount of time, it always does. This is built into special relativity. However, for these virtual particles, it's not that you can violate conservation of energy, but you can give them the wrong amount of energy. I could give that electron only this much energy. It's got to have a minimum of mc squared, but it doesn't. I give it too little energy. And I give it a little bit of momentum too, so I don't make its momentum 0, I make it off here to the right. And then that other particle, the positron, since I have 0 energy budget, I'd better give that one actually negative energy. That's even worse than the electron that had too little energy. I gave that one negative energy. And negative momentum also, but negative momentum ain't no big thing. That just has to do with which direction it's moving. But negative energy, man, that's weird. And you only see it happen to these virtual particles. And you could say the Heisenberg principle there says the farther this thing is away from that energy hyperbola, the briefer a time it will last before nature kind of does the accounting and says, hey, you stupid virtual particle, you're not supposed to exist in the first place. And it says, oops, and disappears back into the vacuum. Now,
so keep in mind we got 15 minutes.
Okay.
Still need to know what the hell is
how does this lead to Hawking radiation? There is actually a method to the madness here. What Hawking pointed out was, hey, that dance of virtual particles, that quantum foam, as somebody mentioned the phrase for it, that's happening everywhere in the universe, including at the event horizon of that black hole. And after some calculations, what he found was if you create a virtual particle-antiparticle pair, so I have got a...
Keep in mind, right big.
Okay, I've got an electron and a positron. This time I'll make the positron outside the horizon. I've got now this electron and positron were born from the quantum foam right at the event horizon. This event took place right mathematically on the surface. What Hawking said was the particle with negative energy definitely cannot propagate out into normal space, but the particle with negative energy can fall into the event horizon. The one that had positive energy can escape out into normal space, and actually it can be promoted. as you kind of shift frames from the weirdly curved space-time around the black hole into the flatter space-time as you move further away, you can take the particle that had positive energy and boost it up to that hyperbola so that it's got the right amount of energy to survive as a permanent feature of the universe instead of just a virtual particle. And meanwhile, because energy conservation does always work perfectly, the one that had negative energy drops even further negative.
So let's review that one more time. So you've got a particle-antiparticle pair popping out of the vacuum.
Particle pair. Let's say this positron has positive energy. Hey, not just because I'm calling it a positron. The question about whether you have positive charge or negative charge, whether you're matter or antimatter, that's totally uncorrelated with the question of which particle has positive energy and which one has negative energy.
We'll
the
get to
matter
that.
can have positive, the antimatter can have positive, doesn't matter. But but what is true is one of those particles that was created from that virtual particle creation event has got to have positive energy. The other one has got to have negative energy. Now again, it doesn't always have to be the positron that has positive energy. The electron, in the example I drew over there, I gave the electron positive energy. But one of them has got to have positive energy, one of them's got to have negative energy, because by having zero energy budget total to create those, so they got to add up to zero. Energy conservation is strictly enforced, always. The universe has no sense of humor about that kind of thing. So, if this happens if this happens anywhere else in space-time, those particles will just simply fall back together, their energy will add up to zero, and they'll be gone. If that happens at the event horizon, you've got this loophole that you can actually let the negative energy particle fall deeper into the black hole, and the positive energy particle can escape to infinity, and its energy gets boosted until it has the correct amount of energy for whatever kind of particle it is. Hey, by the way, if it's an electron and a positron, you've got to boost its energy quite a bit. Most large black holes will not be able to do that, as it turns out. Their event horizon is too cold. However, if this is a photon, a particle of light, then I could create, so for a photon, the energy momentum diagram that I want to have for a permanent photon, instead of looking like a curved hyperbola, it looks like a sharp V shape. So I could give those photons whatever amount of positive and negative energy I want. The negative energy one falls in the black hole. The positive energy one migrates onto that real particle curve. And the net result, well, the black hole just absorbed a particle. So you could say, hey, that means the black hole got bigger, more massive, right? Well, no, because it absorbed a negative energy particle. Those don't normally exist except as virtual particles, but hey, it absorbed that virtual particle that was created right at its event horizon. The black hole's energy didn't go up, it went down. The black hole actually became slightly less massive, and the energy that it lost was carried away by that now perfectly real particle. One of those virtual particles has been promoted onto that graph line where it can be a real particle. Kind of sounds like a Pinocchio story. And
so would you say that the energy came from the black hole?
At least it came at the expense of the black hole's accumulated energy. And yeah, I would say it came from the black hole, because you'd say the particles could not have done this escaping trick if there weren't an event horizon right there, and you wouldn't have the event horizon right there if the black hole didn't have all that energy. So yeah, I would say the energy did come from the black hole. If nothing else, it's always kind of, you'd say, when you're trying to talk about cause and effect in physics, you could say, well, I've got these patterns. I can't really, it's up to me to say where the cause starts and the effect stops and everything. However, I can definitely say, yeah, that you get this dance where virtual, damn it, none of these pens work.
I brought in all my refillable ones.
Oh, did you?
No, over there, no, turn around right there.
Ah, thank you. I used to have a dog like that. You try to point out some object of interest and it would look everywhere else in the room. So I'm channeling my old dog right now. But you'll get this dance of particles escaping from the event horizon of the black hole. Yes, their partners were falling inward of the black hole and carrying with them negative energy. And by the way, these particles for a astronomical sized black hole, these are almost all photons. For a smaller black hole, as you have a primordial black hole evaporating and sending out higher and higher bursts of energy, you will have photons, you'll have gamma rays, which are high energy photons, but you'll also have the whole spectrum of particles: electrons, positrons, muons, anti-muons, quarks, anti-quarks. And again, the black hole doesn't care if it's sending out matter or antimatter. Either one of those can be the thing that it gave the positive energy to. The net effect of all this, if you run the calculations, is every square centimeter of that black hole surface is acting like it's just a radiating surface at a given temperature. And the bigger the black hole is, the colder that temperature. We have never observed Hawking radiation from an ordinary star-sized black hole. We can't. A star-sized black hole has so much mass that its Hawking temperature is tiny. It's immeasurably small. I should have looked up the exact number before I came here, but I mean, it's nanokelvins or probably, I'm probably like making it way too high when I say nanokelvins. So it would be giving off such faint radiation that we're not going to notice. On the other hand, a smaller black hole, a primordial black hole created near the beginning of the universe, a stellar black hole zillions of years in the future when it's starting to run out of mass, or a black hole that was created in a particle accelerator, these can be much hotter surfaces. Well, they will be much hotter surfaces. They're giving off much more energy all at once, and because of that, as the black hole shrinks, it will start shrinking faster and faster and faster because it's radiating more energy until it just shrinks to a point and vanishes. And all the energy that used to make up that black hole is giving off as Hawking radiation. Now, how does that solve that entropy problem? Well, the black hole is now spewing information back into the universe. If I want to tell you how much information the universe contains, I've got to remember to tell you the fate of every one of these particles that was sped out of the black hole over its lifetime. It turns out, if I take that jar of gas we started with and I dump it into a black hole, okay, that particular information in the jar of gas may have been lost to the universe, but the black hole, now that it has more mass, will, over its lifetime, send out more Hawking radiation total, and because of that, the universe will end up with higher entropy, not lower entropy, due to the fact that I have dumped that jar of gas into the black hole. So the second law of thermodynamics is saved. Hooray! Wait a minute, the second law of thermodynamics was not my friend. Oh well, we'll have to make peace with that eventually. But yeah, as far as we can know, entropy does continue to increase.
You want to do a five-minute summary?
Okay. So 5-minute summary.
5-minute summary. What is Hawking radiation?
Hawking radiation is this flux of tiny particles, things that were virtual particles created in the quantum foam at the event horizon, and they have made this wonderful Pinocchio-like transformation into real particles because their negative energy partner fell into the black hole, letting the positive energy particle radiate out into the normal space around it and have the right amount of energy to be on these mass hyperbolae that every real particle has to obey.
I don't know if you can quickly conceptually explain this, but why is it that the negative energy particle has to fall into the black hole?
Because we were saying that negative energy particles cannot exist for very long in normal space-time. So for it not to fall in the black hole, it doesn't have to fall in. It can stay on the outside of the event horizon, in which case it is at the mercy of the Heisenberg uncertainty principle, and it will very quickly annihilate with its positive energy counterpart, and they'll be gone. They'll disappear back into the quantum foam. If the only particle that has a chance of being promoted to a real particle is the positive energy one. So yeah, you're right. You don't have to dump the negative energy particle in the black hole, but if you don't, it'll annihilate the same way every other virtual particle in the universe annihilates. That loophole that lets one of the particles survive long term only applies to the positive energy particle. And again, that doesn't mean positive charge. That doesn't mean antimatter versus matter. It just means whichever one happened to have been created with positive energy at that original quantum foam event there. One other thing, you may have heard of the black hole war, as they call it, between Stephen Hawking and Leonard Susskind. First off, Hawking and Susskind are good friends. The whole black hole war, I've seen some commentators exaggerate it as if these people were out for one another's throats or something like that. No, they're not, but they do have a standing disagreement on the fate of information that's dumped into a black hole. Now, I never understood their disagreement in the past because I said, well, wait a minute. Susskind's saying that information is not lost when you dump things into a black hole. Hawking is saying, yes, I agree, information is not lost. The second law of thermodynamics still applies. The entropy of the universe goes up. It sounds to me like these people are saying the same thing. I mean, I know that they must not be because they both say, no, I disagree with you, but it sounded to me like they do agree. Now, it turns out when I was kind of looking at it further just because I didn't want to be totally ignorant if somebody asked the black hole war question here, and it turns out Susskind's argument is that the specific information in the matter that you dumped in should be recoverable. If I drop that jar of gas into the black hole, it's not just that new information should be spewed out into the universe to replace the information that was lost, but Susskind is saying, if I look at some future state of the universe, I should be able to carefully rewind the laws of physics backwards, and I should be able to find out what was going on in that jar of gas. Hawking's view is, no, that specific information is lost, but the total amount of information in the universe as a whole still goes up. But that the information, that Hawking radiation, replaces the now lost for good information that was in whatever matter you dumped into the black hole. So that's about all we have time for right now, but because I know Joe has to run. And,
I do. How did light come out of a black hole last week? Oh, did you hear about that?
I did not.
Oh, that's a long discussion.
Okay,
And actually,
I will give my 5-second answer. I bet the light did not actually come out of the black hole, but that they're talking about light that was radiated from the accretion disk of matter that was on its way spiraling down to fall into the black hole. I don't even know what discovery you're talking about at the moment. I apparently was asleep at the wheel last week, but I will say that usually when you see a black hole do something macroscopically dramatic, it's not the black hole itself you're looking at, it's the dynamics of that accretion disk of hot matter that surround the black hole. If it was something beyond, I mean, if it really was the black hole giving off light, dude, that's so big that I'm ashamed that I haven't heard about it, but I will read up on it and we can talk about that next week perhaps.
Okay, so thank you so much for joining. My name is Joe. We have just been enjoying listening to Paul Graham. We will be here next Wednesday for episode 10, Ask a Physicist Anything. For those of you who asked, I will post this to my YouTube channel this weekend. It's also on catch.me. If you have questions that we didn't get to, comment on one of the Ask a Physicist Anything episodes. And for those of you asking about Interstellar, Paul did a whole 45-minute rant on the physics of it. And not rant. Okay, anyway, I have to go. Thank you for joining, and hopefully I will see you all next week.
Take care, guys.